Alright, so on this next part, we're going to take a look at using percent composition to actually determine empirical and molecular formulas. So let's break down what those two terms actually mean. So I like to do this with an example. So an example of a molecular formula, there we go, is something like C6H12O6. This chemical we might recognize as glucose, a very common compound. That is its molecular formula. So it's the chemical formula showing the number of each element present in a compound. So this shows us there's 6 carbon, 12 hydrogen, 6 oxygen in an actual molecule of glucose. Its empirical formula is just a formula showing the lowest whole number ratio of elements. So it's just a ratio. It's not actually telling you what the molecule, how it's structured, how many of each element there are. It's just a ratio of one element to another. And it simplifies our molecular formula. So our molecular formula would become CH2O for our empirical formula. And we simplify it by finding a number we can divide all the subscripts by. So we can divide everything by 6, so we get 1, 2, 1 for our subscripts. So to get from one to the other, we divided by 6. If we wanted to go the other way and actually go from our empirical to our molecular, we would have to multiply by 6. So what we can use percent composition to do is actually find the empirical formula, this one, and then we're going to figure out what this multiple is to find our molecular formula. That's the process we're going to be using overall. So what does this actually look like? We're going to take a look at the steps and what the example looks like here. So let's start with the example. It says a 40-gram sample of a compound, some questionable compound, we don't know what it is 50% sulfur and 50% oxygen by mass. So that's telling us our percent composition of each of the elements. We want to figure out the empirical formula. Now it does say calculate the empirical formula. We are going to do a calculation, but your final answer will actually be the formula, not just numbers at the end. So that's something to be aware of. So let's take a look at our steps. The first thing we're going to do is multiply the given mass of the sample, so that's our 40 grams, by each percentage converted to a decimal to find the mass of each element present in the sample. So we're going to take each percentage. So if we're given something like 25.2%, we want to first convert that to a decimal, and you do that by dividing by 100, and that would give us 0.252. So that's what we want to actually multiply the mass by, is if that was our percentage. So in this case, we have a 40-gram sample of a compound, and it is 50% sulfur. So we're going to be multiplying that, but we're going to move our decimal over on the sulfur. Once we have that, we're going to convert the mass of each element in the sample to moles. So we're going to go from grams of sulfur to moles of sulfur. Then we're going to do, actually, let's go ahead and do that, and then we'll go to the next step. So let's just do this. Go ahead and do this part. So 40.0 grams of our sample, and we want to multiply that by our percentage. So 50% becomes 0.500. And basically half of 40 gives us 20.0 grams of our sulfur. So that's step 1. And we want to convert the mass of each element in the sample to moles. So we want to change these grams of sulfur into moles of sulfur. As we've done many times, we want to use its molar mass. Molar mass of sulfur is 32.07, and when we calculate that, we get 0.624, some white out here, moles of sulfur. So that's how many moles of sulfur are in our sample. We're going to do the same calculation, but for our oxygen. Again, this one is 50%, so that's kind of convenient. We know half the sample is going to be sulfur and half of it's oxygen. Now, because sulfur and oxygen don't weigh the same, though, they're not going to have equal moles. So grams of oxygen to moles of oxygen. Okay, and we're looking at individual atoms here. We don't want to do O2. I know it's one of the diatomic elements, but we're just looking at the ratio of one atom to another, so we need to make sure that it's just the individual atoms. All right, so 20 divided by 16, we get 1.25 moles of oxygen. So now we have moles of each chemical. We have taken care of the first two steps. Now, here's this next part. We basically want to find the ratio of sulfur to oxygen. It's hard to write a mole ratio, though, or write a chemical formula. We can't very well write S with a 0.624 as a subscript and an O at the 1.25 as a subscript. That's just silly. So we need to really compare these two numbers. The way we do that is we decide on the lowest number of moles of all the elements present. So we look at the two numbers, we find the one that's smallest. And we're going to divide everything by that number. So we divide 0.624 by 0.624, and we of course get 1 mole of sulfur. And we do the same thing with our oxygen. Divide it by the same number. And it's just giving us a comparison to oxygen. Our lowest one will always become 1, and the other ones will become a whole number of some sort. So we do 0.125 divided by 0.624, and we get 2 moles oxygen. So this tells us that for every 1 sulfur, it is a ratio of 2 oxygen. So what we really want to do is write its empirical formula. So we need to write the chemical formula. Sulfur, we have a subscript of 1, which we don't write, and oxygen with a subscript of 2. That is our final answer. Okay. So let's just take a look at the process one more time. We took our grams of each of the chemical of the sample and multiplied it by the percent composition of each substance. We multiplied them by 100 so that we could get them into a decimal. So we took the grams of each of those, we converted them into moles of each of the samples. We found the one that was the smallest and divided each value by that to find our ratio. And then we're able to write our chemical formula from that ratio. So that's a way to determine the empirical formula. Now this chemical may not necessarily have the formula SO2, but we know that for every 1 sulfur, there are 2 oxygen in that chemical. We know the ratio. Again, this is our empirical formula. Now we're going to find its molecular formula. So remember the example I did up here. The molecular and the empirical are only different by a multiple, a whole number of multiple. So if I want to go from my empirical formula to my molecular formula, I need to figure out which number to multiply by. And there's a way to do that. So let's go down to the bottom. To find the molecular formula, calculate the mass of the given or calculated empirical formula using the periodic table. So whatever we're going to find its molar mass basically for your empirical formula. The problem or the question will provide the mass of the molecular formula, its known molar mass. We're going to divide the molar mass, write a little formula to the side here, scooch this over so you guys can see. We're going to divide the molar mass by the empirical, I'll call it the empirical mass. And we're going to get a whole number. That is that whole number we want to multiply by. So we'll multiply the subscripts in the empirical formula by that whole number ratio and write the molecular formula. So let's take a look at our example. The chemical from example 2, so that was our SO2 that we found before, has a molar mass of 128 grams per mole. So the actual chemical has this molar mass. Remember, this is just our empirical formula. I'm going to put EF for empirical formula. Okay? Determine the molecular formula. So the first thing, we want to calculate the mass of our empirical formula. So 1 sulfur plus 2 oxygen, its molar mass or molecular mass would be 64.07 grams per mole. So that's just adding up a sulfur and 2 oxygen from our periodic table. So as explained earlier, we want to take the molar mass that was given, 128 grams per mole, divide it by this empirical formula mass, and we get a value of 1.99, which we can go ahead and round to 2. We're looking for this whole number here to actually multiply our subscripts by. So now we take our SO2, we multiply all our subscripts by 2, and that's going to give us S2O4, and that is our molecular formula. So it's a pretty straightforward calculation there. All right, I'm going to go ahead and stop this video and do another recording for our last piece.